In the previous video, we saw the intuition behind double integral, and in this video, we are going to make this notion precise. Let f be a function from R2 to R that is bounded on a rectangle AB cross CD. By this I mean the values of the function are bounded above by capital M and bounded below by small m. In this case, we will say that f is bounded on the rectangle AB cross CD. And we are going to define integration only for such functions. As we saw in the last video, the first step is to subdivide this rectangle into smaller pieces. This was called a partition of the rectangle. To do this, we will first partition the intervals AB and CD. Given a partition of the interval AB and the interval CD, we can obtain a partition of the rectangle AB cross CD. More precisely, we will take one of the subintervals of AB and a subinterval of CD and take the Cartesian product of these two subintervals. This will give you a rectangle. And all these rectangles are subrectangles or subsets of the original rectangle. And the collection of these rectangles form a partition of the original rectangle AB cross CD. Notice that there will be n into m rectangles, as I can vary from 0 to n minus 1 and j can vary from 0 to m minus 1. As the function is bounded on AB cross CD, it will also be bounded on all its subrectangles. Therefore, we can compute the infimum and supremum of this function on these rectangles. The infimum on each of these subrectangles will be denoted by Mij and the supremum will be denoted by capital Mij. Then notice that on each of these rectangles, the value of the function lies between small mij and capital Mij. If Aij is equal to the area of Rij and P is the partition, then define L of f comma P is equal to summation Mij Aij, where I varies from 0 to n minus 1 and j varies from 0 to m minus 1. And define u of f comma p to be equal to summation capital Mij into Aij. These quantities are called the lower sum of the function f with respect to the partition P and upper sum of the function f with respect to the partition P. Observe that as small Mij is always less than or equal to capital Mij, the lower sum will always be less than or equal to the upper sum. Now we can ask some important questions. Given two partitions, let's say P1 and P2, what is the relationship between L of f comma P1 and L of f comma P2? Similarly, what is the relationship between U of f comma P1 and U of f comma P2? And finally, we can also ask what is the relationship between L of f comma P1 and U of f comma P2 and so on. So these are the kind of questions that we would like to answer next. If P1 and P2 are completely arbitrary, then we cannot really give a relationship between L of f comma P1 and L of f comma P2. Similarly, we cannot give a relationship between U of f comma P1 and U of f comma P2. However, if one is a refinement of the other, which is something we are going to define, then we can give a relationship. So what is a refinement? Consider two partitions P given by rectangles Rij, where I varies between 0 to n minus 1 and j varies between 0 to m minus 1, and P star given by rectangles Rij star, where I varies from 0 to k minus 1 and j varies from 0 to l minus 1. In this case, we will say that the partition P star is a refinement of the partition P if and only if every rectangle in P star, that means Rij star, is contained inside some rectangle in P. Let's call this rectangle Ri dash j dash. Notice that I and I dash can be different and j and j dash can also be different. Let us look at an example of refinement. Given a rectangle AB cross CD, recall that a partition is given by a partition of the interval AB and the partition of the interval CD. Therefore, we can obtain a refinement of the partition of the rectangle by taking a refinement of the partition on AB or the partition on CD. In this case, let us take a refinement of the partition on AB. More precisely, we are adding just one extra point between xi and xi plus 1. This will result in a finer partition than P. In other words, P star is a refinement of P. To give a concrete example, consider a partition of 0, 1 given by 0, half and 1. Then you can take a finer partition given by 0, half, 3 by 4 and 1 and 0, half and 1. In a similar fashion, you can construct more examples. And I urge you to play with it for a bit. Recall that given two subsets A and B of the set of real numbers such that A is a subset of B, infimum over elements in A is greater than or equal to infimum over elements in B. Therefore, as Rij star is a subset of Ri dash j dash, you can notice that Mi dash j dash has to be greater than or equal to Mij star. Why? This is because the set of all f of x such that x belongs to Ri dash j dash contains the set of all f of x such that x belongs to Rij star. Further notice that the rectangle Ri dash j dash will be union of some rectangles in the partition P star. And for each of these subrectangles, the same relationship holds. Thus, with some algebra, we can show that L of f comma p is less than or equal to L of f comma p star. That means the finer the partition, the higher the lower sum. But supremum has the opposite behavior. Supremum over a bigger set is bigger. Therefore, we can conclude that Mi dash j dash is greater than or equal to Mij star. And this would imply that u of f comma p is greater than or equal to u of f comma p star. In other words, the finer the partition, the smaller the upper sum. But one question remains. Given two partitions, how does the lower sum of f with respect to one partition compare with the upper sum of f with respect to another partition? This is the question that we will address next. For this, we require a trick called the common refinement of two partitions. But before that, let us simplify some notations. So far, we have been denoting a partition of AB cross CD by a partition of AB and a partition of CD, and we were representing the partition of AB and CD by a list of ordered points between A and D. But given such a list, I can represent it by a subset of AB and a subset of CD. As soon as we have the subset, we can order them automatically. So the ordering is not important, only the subset is important. Therefore, we can represent a partition by a subset A of A comma B and a subset C of C comma D. However, there is one property that these subsets should satisfy. Namely, the elements A and B should be contained inside capital A and the elements C and D should be contained inside C. Given this simplified notation, now consider two partitions. Let Pi be the partition given by a subset Ai in A comma B and Ci in C comma D, where I can be equal to 1 or 2. Given these partitions, I can consider a common refinement of these partitions given by P. How do I define P? I take the subset A1 union A2, which is a subset of A comma B, and C1 union C2, which is a subset of C comma D. Notice that A1 union A2 is a refinement of AI for both I equal to 1 and 2, and C1 union C2 is a refinement of both C1 and C2. Thus, the rectangles in P will also be contained inside rectangles in P1 and P2. In other words, P is a refinement of both P1 and P2. This is called a common refinement of two partitions. Recall that a finer partition means higher lower sum. Therefore, L of FPI is less than or equal to L of FP. But the lower sum is always less than or equal to the upper sum. Therefore, L of Fp is less than or equal to U of Fp. And finally, a finer partition means lower upper sum. Therefore, U of F comma P is less than or equal to U of F comma Pj. Thus, we have shown that the lower sum with respect to any partition is less than or equal to the upper sum with respect to any other partition. So it doesn't matter on the partition. Given any two partition, the lower sum with respect to one partition is less than or equal to the upper sum with respect to the other partition. Thus, the set of all lower sums is bounded above. Any upper sum forms an upper bound for this set. Therefore, as this is a subset of R that is bounded above, we can find a supremum of this set. And the supremum will be called the lower integral of this function on the rectangle AB cross CD. Similarly, you can observe that the set of all upper sums of this function is bounded below. More precisely, it's bounded below by any lower sum that you take. As this is a subset of the set of real numbers that is bounded below, we can take the infimum of all these values. And this infimum will be called the upper integral of this function on the rectangle AB cross CD. We say a function f is integrable if both the upper integral and the lower integral are equal. Moreover, this value would be called the integral or the double integral of this function. Observe that this is somewhat impossible to compute, right? Because we will have to compute all lower sums for all partitions and then take the supremum and so on. It's too much to do. So in the next video, we will discuss a method that will enable us to prove integrability of various functions.